Okay. All right. Linearity. All right. So it took me a couple of minutes. Sorry about that. Question? Have you been doing No, I just started doing that today. Last lecture, I used your homework as attendance. And if you submit it online, I'll count that as well. Okay. So yeah, make sure that you sign the attendance that's going around. And this is what we're going to cover today. Before I start, is this big enough for everybody to see? Is it too small? That's a better question. No, my vision's not perfect, huh? All right, cool. I like that. Give me a chance to sit down too. It's very hot outside today. All right, so last time we talked about separable equations, right? You guys remember that stuff? You know, bringing the variables to one side of the equation and then you just integrate. Okay. So now we're going to talk about a type of equation that's similar, not too much more complicated, but it's complicated in such a way that you can't just bring variables to one side and integrate both sides. And these are the linear equations. They have one extra term that kind of messes things up for us. Oops, sorry, I have to do that. So let's see what these look like. Quick outline, we're going to talk about linearity again. It's an important property, we need to know that. And then we'll see some examples, and finally we'll see a general solution, like what all these examples have in common, and whether we can derive the formula that I'm going to give you. Okay, so what do linear equations look like? They look like this. Linear ones on the left, non-linear ones on the right. And we've seen some examples of this before. Remember where we plugged in sum of two functions and we checked, all right, does this end up looking like the sum of two differential equations? Okay, so I claim the things on the left are linear, the ones on the right are not linear. And you can maybe guess that because there's a y squared and a sine y dividing by y, but the left side doesn't have any of that. It just has sums of derivatives of y. All right. And in general, that's what an nth order linear differential equation looks like. Notice that those coefficients are functions of x. So a sub n, a sub 1, a sub 0. Those things can involve the variable x. They cannot involve the variable y. And then we have this extra term on the end, b. That's usually called like a forcing term. Sometimes it is called like a signal if you're doing some sort of engineering class. So maybe you'll see that at some point in a different course. All right, but we want to try and solve these things. In particular, we're doing first order equations, so we want to solve the first order linear equation. We'll get there. But so what does it mean in general? So we call functions linear, not usually equations. We sometimes call things linear equations, but what's really linear is the function part. The fact that we're applying some rule to a variable x and getting out something that behaves in a way that preserves straight line structure. All right, so the function is this sequence of operations giving rise to the differential equation. So something like this. And usually we call those sequences of operations differential operators. Okay. So the derivative itself is one example of a differential operator. Something else like this that does multiplies something by minus 1 over x squared, and then takes the derivative of that same thing and multiplies by 1 over x, and then subtracts those two things. That's a differential operator. Right? It does that to y, and I shouldn't have written the y there. So L is a thing that eats functions, outputs other functions, just like the derivative does, or the antiderivative. All right, questions here? We good? Cool. All right, so what does linear actually mean? So a differential operator is called linear if for any functions y1 and y2 and any real number alpha, we have two properties. So additivity, you might remember this. If you plug in a sum of two functions, it's the same as doing all of those functions, and then adding the results together. The other one is called homogeneity. And it just means, okay, you multiply the input by something and it's the same as multiplying the output by the same thing. You don't get any weird variation in different for different outputs. Okay. Little footnote here. You can have things that satisfy one and not the other, but they're hard to construct. So generally you will see anything that is additive will also be homogeneous. It's very, very rare to see anything that's one and not the other. Okay. Here's an example. Let's show that the previous operator is linear. I'm going to let you guys try this one for a minute. Let's go back to the operator so you can see it. So take this operator and show that this thing is linear. Show that it has the two properties. Give you a second to write this down, and then I'll go back to the properties so you can see them. It should be additive and it should be homogeneous. Okay. Let me go back to those properties. Okay. So make sure that that operator has those two properties. Let's say go until 4:13. Give you 4 minutes for it. If you're just walking in, by the way, make sure you sign the attendance sheet. No, just today.
Where is it at?
Somewhere around here. Okay. Check if you're showing that it is. Make sure that these two things are true for that function. Anyone else need the attendance? 1 second. Note that when I write this operator down, you can think of this part as multiplying by 1 over x. So you multiply the function y by that. And then in the first part here, you want to take the derivative and then multiply by that. Hey. Everyone has it now? Attendance? All right. Anyone have any good ideas? Get somewhere? Anybody get completely stuck? Don't even know where to start? Yeah. Okay. So let's try this. Let's try this together. So let me write down our operator here. It's L equals 1 over x ddx, and then minus 1 over x squared. And so when I plug a function y into this operator, it should look like L of y equals 1 over x d dx minus 1 over x squared applied to y. And that means do this. Take the derivative of y multiplied by 1 over x, and then subtract 1 over x squared times y. Okay. So if we want to show that this function is additive, what do we want to do? Well, we want to take y1 and y2, and we want to compute L applied to y1 plus y2. Okay, so this works just like function evaluation for regular functions. Everywhere that you see y in the input here, you just replace that letter with the thing that's being plugged in. Okay, so I'm plugging in y1 plus y2. Everywhere I see a y here, I'm going to replace it with that. So we have 1 over x d dx of y1 plus y2 minus 1 over x squared y1 plus y2 times y1 plus y2. Okay. And now we can distribute things. So here we can distribute 1 over x squared to y1 and y2 because that's multiplication, right? And then here, why can I distribute all of this stuff? Why can I write dy1 dx plus dy2 dx? Isn't this a property from Calculus 1? That you can take the derivative of a sum and it's the sum of the derivatives? Okay, yeah, so we're using stuff that we know from previous calculus classes. Right? And then we're checking that this new thing that we're learning works just because we know that already. Okay, so yeah, we can do that. And then the 1 over x here distributes because it's, again, just multiplication. So we can write 1 over x dy1 dx plus 1 over x dy2 dx minus 1 over x squared y1 minus 1 over x squared y2. And now we can group up terms in corresponding colors. And those will look like, in blue, L of y1, and in red, L of y2. Oh, that should not be minus, that should be a plus. Okay, so that additive property is satisfied. Let's just go back and check. Okay, additive property says I plug in a sum of two things. I rewrote things a little bit using algebra and some calculus properties that I knew, and I got, yep, the sum of the derivatives, okay, with some extra stuff thrown in. All right, so it's additive. Let's check that it's homogeneous. All right, so here, we're gonna start with the left side of our property that says, all right, plug this in, and then see if you get this out. I'm just gonna put alpha y here. Then I want to carry a subscript. All right, well, that means I do 1 over x dx minus 1 over x squared. Apply that to alpha times y. And now, all right, well, I apply each part of the function to y, or alpha y. It's kind of like distributing alpha y in, right? Except I can't distribute it on the left side. I have to make sure that I'm applying the derivative to it first. All right. And now, okay, what's another Calc 1 property that will help me out here? Alpha is a real number, y is a function. I'm taking a derivative of that. If alpha was like a 2, what would you do? You can take it out front, right? So alpha, because it doesn't depend on x, can come right out front. And so we would write alpha 1 over x dy dx minus alpha 1 over x squared y. And then we can factor out alpha from everything. So we'll have alpha times 1 over x dy dx minus 1 over x squared y. And that looks like L of y. All right, so yes, that operator is linear. Note that we did have functions of x as coefficients there, and that didn't mess anything up because we're plugging in for y, not x. Right? The variable is the function y now. Right? So here's an example of a not linear operator. I should have changed the title of that slide. Okay. So if I go back a little bit real quick, note that that operator that I wrote down is really just this equation where I've subtracted y squared over. That sort of trick pops up once in a while, so it's good to know. All right, so let's check that this is linear. K of y1 plus y2, or is not linear, sorry. This says y1 plus y2 prime minus y1 plus y2 squared. Okay. So for the first term here, I can do my derivative property. Derivative of a sum is the sum of the derivatives. So y1 prime plus y2 prime. Okay, that looks pretty linear. Good sign. What happens over here? This I have to write as y1 plus y2 times y1 plus y2. All right, you help me out. What is that multiplied out? Awesome. Yeah, we just go ahead and FOIL things out. And, ooh, okay, I do see the terms that I want, y1 squared and y2 squared. So I have, if I rewrite this a little bit, y1 prime minus y1 squared, not y2. Okay. Plus y2 prime minus y2 squared. Oh, but then I have this extra term that is the product of those two functions times 2. So this is k of y1 plus k of y2 minus some extra stuff, and this extra stuff makes it not linear, right? We did not get out just this. So this would have made it linear. That was all we saw. But this extra term makes it not linear. Do we understand that part? All right, good. So moving on to our next section, we want to start solving. Sure, yeah. So the next thing that we want to do is start solving first order linear equations. And we'll do that with a few examples to kind of build up our intuition, and then we'll see what we can do to solve a differential equation of this form. Okay, so let me write something down here real quick. We had, in general, differential equations that looked like this, right? Equals b of x. And then down here, I have something that's written a little bit differently. So what I've done is I've just divided through by that leading coefficient, a1 of x. And now p of x is a0 over a1, and q of x is b over a1. And those end up down here. You can always do this. Sometimes you'll have to worry about a1 of x being 0, and there are ways to deal with that. But we want to think of linear equations just kind of naively as being writable in this form, because that will help us later on. Okay, this is called standard form, and that's what we're going to solve. So we start with linear equations, look like this, rewrite them to look like standard form, and then we apply our solution method. So here's a formula that you can use to solve any first order linear differential equation. I'll give you a minute to write that down. I'll explain it. So first, it's 3 steps, 1, 2, 3. You want to write it out in standard form. So if you're given a differential equation, you can maybe check that it's linear and you see, okay, it's first order. Then you should be able to rewrite it in standard form as that previous equation. So you want to do that first. And then once you have it in that form, you want to compute this extra thing called the integrating factor. And that just depends on that p of x coefficient. So you want to take that thing, find its antiderivative, and then use it as the exponent for e. That is your integrating factor. Oddly enough, integrating here does not refer to that integral. It refers to a different one. Okay. Once you have that thing, your solution is this formula. Okay. And in general, as soon as you realize that a differential equation is first order linear, you want to just compute that, write this down. You don't want to have to go through the steps of deriving the integrating factor every single time, because it's tedious and you don't need to do it more than a few times. Once you know the process, you know it, and you can just start writing down solutions if you can classify differential equations. The point of all this work is to make things easy for us, to do some of the hard work in advance so that, all right, I've seen this before in my diff-EQ class. Now I'm doing it in, I don't know, thermodynamics, and I know the solution to this thing without having to do a bunch of work. Okay, so given that formula, let's try an example. So I'll give you a few more minutes to do this one. Let's say until 4:32. So try to use that formula to solve this differential equation. Go through steps 1, 2, 3, and see what you get.
That's the only reason.
Okay, so I give you a little bit longer, but let's go ahead and do this together. All right, question? Yes. So standard form is this right here. So a couple of you got some help, and I told you that you want to try and rewrite it this way and then classify P and Q first, figure out what's P, what's Q. Did anybody get further than that? No? You got somewhere? Okay. Well, I want a solution, right? I want y of x. All right. Let's work on it together now. Okay. So you got somewhere. What did you get out of the answer? Let's check that. One over e to the what? 1 over e to the log absolute value x. Not quite yet. There's one thing missing. Did you get that? Okay, so there's something here that we're going to fill in. Yeah. Oh, for the integrating factor. Okay, yeah, the integrating factor is e to the log absolute value x. Yeah. Okay, yeah. That's exactly it. Yep. Now you can actually compute that antiderivative, so we can simplify this a little bit. But let's go ahead and get there first. So, come on. Do I have an extra page? No, I didn't. I didn't give myself extra space. All right, so our step 1 says rewrite it in standard form. So standard form is going to be take this term, bring it to the other side, right? Because this is the term that involves y, and this term does not involve y. The trick is that they're added together or subtracted, right? There's an additive relationship between all 3 of these terms, and I can add that to the other side and make it look like standard form. So maybe we'll write that down actually as well. Standard form looks like this. Okay. So for this differential equation, our standard form is dy dx plus y over x, okay, equals 1. And then, well, we actually have to write 1 over x separately so that we can recognize this is p of x, and then this is q of x. So p equals 1 over x, q equals 1. All right, step 2. That was our integrating factor, right? So we want mu of x, and that was this formula. Now we know what p of x is because we wrote things in standard form, and we can just plug in. So e to the antiderivative 1 over x dx. And that antiderivative is log absolute value of x. Okay. And there's a reason I'm not writing plus c here. It's because it doesn't actually matter in this case. But using that, we can now just write down our solution. 1 over, oh, wait, don't e and log cancel each other out? Yeah, so this is absolute value of x.
Why is there a plus c at the end?
Okay, we can write the plus c. We'll see what happens to it. So there should be a plus c right there, and that'll give us e to the c times absolute value of x, and then this we can just choose to be any constant we want, right? So c absolute value of x. Okay. And then here we have, okay, we need our integrating factor as well over there, c absolute value of x, and then times q of x, which is 1. Yep. All right, and then plus, let's call this, I don't want k there, maybe d for another constant. So what happens here with this c? Cancels out, doesn't it? Yeah, because I can bring it out front of the integral. So this cancel out, and now I just take the antiderivative of absolute value of x. So that's a little weird because that's not a differentiable function, right? Except it's not differentiable at 0, but everywhere else it's differentiable. So may not have seen it before, but the antiderivative of absolute value of x can be written as a piecewise function. So x squared for x greater than 0, and negative x squared for x less than 0. And then right at 0, usually we just say, all right, maybe it could be exactly equal to 0, even though it's not really defined there, or the derivative isn't defined there. Okay, and so our solution looks like this: x squared minus x squared plus d. Okay, and if you want, you can distribute the 1 over absolute value to each one of those. And you should get, what is x squared divided by absolute value of x? Not something nice. So, actually, yeah, that's, okay. This is x and minus x for, you can go through this and check if you want, but this ends up just being x. Okay, so that's using the formula. So in general, we have a question. Mu of x? Q of x is whatever ends up on the right side here, which I've written as h of x in this one. Yeah, you can write it out in general once we do the solution for the whole thing at the end, and then you'll see, okay, it always cancels. All right, so here's our observation. If I write a first order linear equation like this, and then I notice, well, g of x, if that was the derivative of this thing, this would look like the product rule, which should have had, okay, yeah, that's a mistake. That shouldn't be there. It would look like the product rule, so that we have, what in the world did I write there? Oh, I see what happened. My bad. This was supposed to be equals f of x dy dx. Okay. Yes, it looks like the product rule. On the right side, we have, all right, derivative of y times f of x plus derivative of f times y, and then equal to some extra function on the other side. That's the derivative of f times y. That's another one of our Calc 1 rules that we learned. Okay, can we extend this? Can we keep doing this trick for other examples of first order linear equations? Yes, we can. Why do I have 2 of these? Don't know. So let's try that with an example. And I'll do this one for you. So let's see. I have dy dx plus 2y equal to 4x. Okay, well, 2 is not the derivative of 1. So as written, this doesn't quite work. But if I use a clever trick and multiply by e to the 2x, then my differential equation looks like this. Okay, and why is this a clever trick? Because now this is the derivative of that. Right? If I check ddx of e to the 2x, well, I got to do chain rule there. Derivative of e to the 2x is itself times derivative of 2x is 2. Yep, that works. Okay. So I multiplied by a new function that I just knew, but we'll see how to get it, and ended up with something that looked like the product rule on the left side. Okay, so then that gives us the ability to write this as d dx of e to the 2x times y. Remember, this was the derivative, and this is the original function. Right? So we want the undifferentiated part times the undifferentiated part. Okay. And that's equal to 4x e to the 2x. Move that over a little. Okay, and now we can go ahead and integrate. So on the left side, these two just cancel each other out. Right, that's the fundamental theorem of calculus at work. And on the right side, we might have to do some integration by parts for that, but that's okay, we can do it. So here we have e to the 2x times y equals, and then integration by parts, we've got 2x e to the 2x minus e to the 2x, I think. Integrate again. Yeah, that should work. And then plus C. Okay, so here we get 2x minus 1 e to the 2x plus c. All right, we're doing okay up to this point. So we've gotten through the hard part, and now we just have to solve for y. Question?
So for the e to the 2x, you just came up with that. As you do, work out.
Yeah, I knew it would work, but I'll show you how to get it in the next example.
So, I don't know, it might be explained in the next example, but it's generally speaking, e to the something x, like a tool you could use.
Sort of, yeah. It's e to the antiderivative of something.
Right, okay.
That's where the integrating factor comes from. Okay, so let's go ahead and solve this real quick, just get our final answer. 2x minus 1 plus c e to the minus 2x. Ooh. Notice now that c is multiplied by something that involves x. Okay, so we might get some answers out for c depending on initial conditions that are not just, all right, plug in here and get a bunch of stuff canceling out, and then c just equals something. Now we might have to do a little bit of solving for c. Okay, so there's our general solution. Yeah.
You had 2e to the 2xy. Where did that 2 go? I'm just
With
where it's like,
oh, this one?
yes, where did that 2 go?
It went into the derivative. So if I take the derivative with respect to x of e to the 2x times y, I do product rule, right? Okay, so first term derivative is 2e to the 2x. Then I multiply by y. Plus e to the 2x times derivative of y. Right? Yeah, so it pops into the derivative over here.
Thank you.
Any other questions like that? Okay. I thought I might need more space. We didn't. Okay, so here is how we solve this in general. So we want to solve standard form for a first order linear differential equation. This thing. For any choice of the functions p and q. All right. My claim is that we can't do this all the time. And the reason is that we have to be able to anti-differentiate p, and we have to be able to anti-differentiate q. We saw that in the formula. We saw integral of p as the exponent for e, and integral of mu times q is part of the solution formula. So those things have to have antiderivatives. That doesn't always happen. These functions have to be something called absolutely continuous in order for that to be true. Now, almost every function that we'll deal with here will be absolutely continuous. But if you go on to more advanced math classes or sometimes physics or engineering, sometimes those things pop up. So how do we do this when we assume that the functions are nice? Well, we multiply by this function mu of x. And we don't know what this is yet. So I just multiplied and said, all right, hopefully there is some function that works. All right, well, now I just have a slightly more complicated looking equation. What do? Well, I make this note. It would be really nice if I had an equation that looked like this. That was what we just did with our observation. We said, all right, this thing should look like the product rule. Well, what would be required for this to happen when I have this equation? I would require these coefficients to be equal, and that's how I get this. This differential equation is separable. So that technique we learned in the last class can be used to solve this differential equation in general. Okay. Let's see how that works. So over here, it's a new differential equation. Derivative of mu with respect to x equals its product with p. Okay. So I can separate variables, bring the mu over here, and p of x over there with the dx. And now I take antiderivatives on both sides. Here I get log absolute value of mu. Here I get antiderivative of p because I don't know what p is, but I can still write this formula down. And then, well, I go ahead and take the base e for both sides. And I drop the absolute value because I know the constant's just going to cancel out. That's how we get our integrating factor formula. So the motivation for finding this integrating factor is the product rule. And then in doing that, we multiply by this function mu, we get a new differential equation, and then we can solve that using separation of variables to get our formula. Okay. So now if you ever forget the formula, hopefully you can at least remember the ideas that you need to use to get it. All right, now what? Now we want to solve our differential equation. So we had, it looked like we had mu dy dx plus mu x p of x times y equals mu times q. And we wanted, or we made sure that this thing was equal to the derivative of mu. Okay. And so that allows us to rewrite this part as d, let's do that in blue, d dx of that's not what I wanted to write, sorry. I wanted to write mu dy dx plus mu prime y, and then undo this using the product rule, and we get what's next in the display. Okay. All right. Now do what we did for the last example. Antiderivative of both sides. Here, the derivative will just cancel out. And over here, just write that big integral sign, right? And I should have had a plus c there. But... And now, there's our formula. Okay. So the ideas are just Calc 2 or Calc 1 stuff. Sometimes you have to do a little Calc 2 stuff to get those. But those big nasty formulas that you thought you had to remember, you don't. You just have to know those two tricks to figure this out. All right. Questions before we move on to this last example? All right. Now that we've seen a few examples of this, we've worked through some theory explaining it. We'll give you the 7-ish minutes, maybe 10, to see if you can figure this one out on your own. You guys can talk to each other, but I won't help you until last 5-ish minutes or so. It needs to not have y in it. Mhm.
Yeah, like, it's just like a there's a possibility.
All right. Got a few minutes left. Let's go through this real quick so you can go home and do the homework that you're very excited to do, I'm sure. Yeah. Yeah. I like hearing that. Yeah. I mean, the next DEs class you guys take, you'll be excited for Fourier series and all of that stuff, right? Boundary value problems. It's great. I'm excited for you. All right, let's go ahead and solve this then. So I'm going to use the other page since I gave it to myself. 1 over x dy dx, and it's minus 2y over x squared. All right, and then our forcing term over there is x cosine x. All right, so is this in standard form? No, good. So not in standard form. That means we need to rewrite it as, okay, standard form has leading coefficient 1 right here, right? So we want dy dx, and then multiply through by x, we get minus 2 over x, y. And I wrote it this way because now that's p of x. And then x squared cosine of x right there. Okay. Find our integrating factor. So this is going to be e to the absolute value, or, sorry, not absolute value, integral minus 2 over x. Okay, that's just my formula, right? I can go through the work to get that if I need to, but I remember that for now. And that gives me e to the minus 2 log absolute value of x. Okay, and well, I want to cancel the e and the log, so I'll use some log rules. That'll give me 1 over absolute value of x squared. And since it's squared, I can drop the absolute value. So 1 over x squared is my integrating factor. Okay, so I multiply through by that, and let's see what happens. I get 1 over x squared here, dy dx, minus 2 over x cubed, y, and then, oh, look at that. The x squared cancels out, and so I don't need to do integration by parts. Whew. All right, so if this is mu and this is mu prime, I get to write, where is it? D dx mu times y. And now I just integrate both sides and I get mu of x times y. Mu was 1 over x squared times y equals antiderivative of cosine. Plus c right there. And we get, what do we get? Antiderivative of cosine? Sine, good. Sine of x plus c. All right, and then we go ahead and solve for y. We get x squared sine x plus c x squared. All right, and there we go. There's our solution. All right. We are done. If you have any last minute questions, I'll be here for a minute or two. Sorry? it just stays C here because we're finding a general solution. We don't have any initial conditions. Once we have initial conditions, we'll get a C value. One second.